confused why we are studying these courses. They know what they will be doing. Still, by the time someone says in between and they got confused, and maybe they will be changing their directions also. So with this, I will ask you to, sir, please start with your talk. And I hope you will be having a great talk and interactive session with the student.
Thank you, sir. I will start sharing the screen. Are you able to see the screen now? No, now it should work.
Yeah, it is visible now.
Yep, I can see it. Okay, I think we can start then. Thanks. First of all, thanks for the kind introduction and the welcome from the head of the department. And I'm so grateful and so honored to being invited to speak to these engineers, as you said. Yeah, it's very important to motivate or to make aware of your students, like why they are studying it, not only what they get after it, like what they can contribute with their professions or with their educations that they spend a long 4 years, especially during this tough time of Corona, all the circumstances. So I'll try my best. So I made the presentation in a way that's more focused on the students with the simple basic stuff. So it's not going to be a very difficult presentation for the people who joined. So still people are joining, so we can slowly start. So first of all, this presentation is happening for two reasons. So here you can see a picture that was, let me, if it doesn't go as the way I want. Yeah. So it's a picture that was taken 8 years back. So there you can see there was the day of convocation of my master's. You can see the guy next to me. So that's your teacher, Dr. Ridesh Palkar. So he was doing his PhD back then. So we had a chat after a long time. I think since this photo was taken, we had a chat a few weeks ago. Then we stumbled upon like giving a talk or having a discussions with the students of your university. So that's how it happened. So with this, like who is his physical appearance, like his passion for motivating others hasn't changed. It's only got better. So I'm very happy to see that you got him in the university. I'm sure like other faculties, they will definitely play a role in catalyzing your journeys to your goals and passions, your dreams of becoming a professional engineer and moreover a socially responsible engineer. So that's the first thing. And second reason, of course, we know it's the coronavirus. So the flip beneficial side of the coronavirus, we actually started exploring the possibilities of virtually connecting, virtually reconnecting, virtually educating, or getting access to more information all across the world. So due to Corona, like we are meeting now from our living room, kitchen. I'm meeting from my child's room. So it's actually happening. So these are the main two reasons. So today, what I would like to do with the presentations, so you can see maybe your face goes like this during the presentations. Initially, it's a simple thing, and as we go towards the end of the presentations, we'll be horrified. So no, that's not the plan. So let's keep it really simple because our title is Process System Engineering, and the subtitle, what the undergraduate student must know. So the main objective of this presentation is to give you a simple basic ideas what exactly the process system engineering, and to enable you already think about you already doing something in your undergraduates that's so relevant to the field. And secondly, to make next steps, as your head of the department was saying, to make your next steps after your undergraduation, or to make plans in your studies if you're really interested in this area of process system engineering. and also to collaborate or to connect with the people who are working in this field if you're interested. So you can expect a little bit like what these people are doing on this field, or what nature of work they are doing in process system engineering. So we'll keep it very simple and to the basics and very short. So if we can make the following section of discussions very well. If you have some generic questions also, so welcome, because the presentation is going to be very generic, no rocket science. So going to the first part, I would like to keep it in a two-way discussion. It's very difficult in a virtual discussion, but if you like to speak up, you can unmute and speak up. So the first question I may ask you is, who is a chemical engineer? So if you can define in a single sentence, the students, you're already in this field, or you're trying to explore the fields of chemical engineering. So how do you define a chemical engineer in a single sentence? So maybe I give you 10 seconds. I can start with, I can give you a hint. Chemical engineers are who, then you fill in the blank. And if you're shy or if you're fast enough to type, you can also use the chat. Yep, that's 10 seconds. So that's fine. So that's also a test to see the activation energy of the group. So it shows like the required activation energy is quite high. So I have to operate this presentation at higher temperature, right? So that's a analogy you can. That's a simple analogy, but that's fine because it's very common. It's not a problem even for myself. Like when we're in a conference, when we are in a meeting, sometimes it's difficult to speak up, even though you have ideas, or even though you have good questions, or all the questions are good. You feel like something is really pulling you back. So that's normal. That's a very human thing. But there is always room to improve this stuff. So this is also should be part of your education. It's not only these technical stuffs and terms and equations, also the personal skills in order to show your presence in a meeting or gathering, or to show your contributions when you get together to solve a problem. That's equally important. But that's all the time. Everyone is struggling with that, so no problem. So maybe some of the guys already Googled what is chemical engineering. Then you have seen this just now. So there you can see the year 1887. So something happened on 1887. So these were the first series of lectures, like 12 lectures given at University of Manchester by George E. Davis. He is known as the father of chemical engineer. So that is kind of a start of the chemical engineer. As far as I know, the first individual or a separate discipline of chemical engineering have started at 1908 in the same university. So what happened during this time, everyone knows this story. So it's due to the Industrial Revolution. So due to the Industrial Revolutions, the demands for the products have been changed, because until then, people were making things in bulk quantity, not worrying much about the quality, but quality was not that strict. But after the Industrial Revolutions, the applications were enormous, and they needed to meet the strict quality of the product when they produce things in large volume. So until then, back then, mechanical engineers were really taking the control of the production process, and the chemists were doing all the laboratory stuff to see how the chemical reactions are working out. So they approached a chemist to do this, and then he said, "Oh, I can do all this in a bench scale or with my beaker and pipette, but I'm so scared to do it in a large scale." So when they approached the mechanical engineer, he said, "Okay, I can do this, but I don't know exactly how to engineer these chemical reactions or the chemistry behind these reactions." So back then they did a sandwich of both, the chemist and mechanical engineer. So the main idea is to produce things in large volumes at the same time maintaining strict quality of the product. So that became a chemical engineering discipline. So what chemical engineers do, they produce things in large volume by maintaining strict quality. So how we do it, of course, the central part is the chemical reactions. So you need to produce B and you have a material A, But it's not only the reactions, you have two auxiliary steps. The first one is the pre-treatment. So you need to make this raw material ready for the reactions. For example, that's what you learn in your subjects like mechanical operations. So you see process like size reduction. You need to feed this A in a particular size, or you need to wash it or dry it. All this sort of steps happening here in the pre-treatment. And once the reaction happens, what happens, you're trying to convert A to B with a chemical reaction so that B is produced, but not all A is converted to B, so some is left over there. And there could be some byproducts or side products that was not intended. But what was the demand after the Industrial Revolution? You need to produce things in a stricter quality. So you need to purify your product, the required product. So there comes a post-treatment step. So mainly the separation steps, most of the things that you learn in your mass transfer operations, how to separate one thing from another. So you separate your product from other unwanted things, like it could be the unreacted reactants or the side products. But how do we make profit? Because chemical engineers or any engineers has to make profit with their problem solution. They shouldn't run into a problem that lead to a loss. So how we make profit? Because this B is really value added. Its price is so high compared to A, and all the production costs that you require for each step. So basically, this was a call back then that evolved into a different discipline of chemical engineering, where engineers produce things in large volume from cheap raw materials by maintaining the quality of the product. So there could be like a different or more than one processes develop, or many or multiple processes develop, so that we make profit. So you make things that is value added from the cheap raw material. So that's the story in 1908, how chemical engineering was evolved as a separate discipline. So the next step, what is process system engineering? So this is an interesting definition I heard when I joined, when I took a course in my master's at NIT Warangal. So the definition is how the process would behave if it was constructed. So it's a kind of a prediction. You're predicting, there's no system already, there's no physical system already, but you're sort of predicting how that would be if you construct the system. But why the prediction is important? So I just went to your website where you see the outcomes that students should achieve while they complete or going through your program. So one of the important, one matching very close to this, I found here, like it's the course expect you to be proficient to predict possible outcomes or the consequences of any situations or the problem in hand. So the prediction is important. An engineer should be able to predict, but why it's so important? So this term actually was, the term of process system engineering was first proposed in 1982. So you know that chemical engineering as a discipline was out there in 1908. It took like another 80 years, 8 decades to understand, or 8 decades to realize that we need to predict things. So Professor Roger Sargent is known as a undisputed father of this. He was the one who was really trying to emphasize the significance of process system engineering in 1982. But what's happening during that time? So here you see, if you know, in 1970s there was a huge oil crisis, especially in the Western world. There was a shortage of oil and gas. So that actually made them to think about how to make the existing process more efficient. So maybe you know about the company Aspen Tech. So they have products like Aspen Plus, Aspen Highs, many simulation softwares, modeling and simulation softwares. But if you look back the history of Aspen, that was actually a research project. That was a 4 to 5 years research project, and this was a paper published in 1979. So if you don't know the full form of Aspen, it's over here. So it's an advanced system for process engineering. So the main idea back then, because until then, from 1908 and 1980, most of the plants across the world, they were taking the resources for granted. They were getting the fossil resources. They're just converting it, selling their product and making profit. So everything was so nice. But when they had a shortage of the raw material or the resource, then they actually there was an alarm like, okay, there's a problem. If there's a shortage, we shouldn't take these things for granted. So then that was a call in 1980s or 1970s to make the process more efficient in order to efficiently use their resource, could be energy or the material. So the interesting thing you can read here in the abstract, if you can read it, that says this is a next generation process simulator and economic evaluation system. So even then, like all other engineers, we are just focusing on the profit, how to make profit, because if you make your process more efficient, you can deal with all the uh, shortage of this feedstock, and at the same time, it makes your process more profitable, right? Because when you make things efficient, you need less raw materials, less energy. Your operating costs would really go down. You can operate things in a smaller size. Your capital costs would go down, so the total production cost would be less compared to what was before. And also they say the system is presently under development for use in engineering for fossil energy conversion process. So still, that was a time we were hugely, or even now, like the majority of our needs are met by the fossil-based processes. But now you can see the Aspen how it's evolved over a time. It's not only the fossil energy for the fossil energy conversion process. It's not only the economic evaluation system. They have a whole bunch of product. If you have license to Aspen in the university, you can see Aspen Plus, HYSYS Dynamics, and for cost estimations for the heat exchanger network. So for almost all the applications to make your process more efficient and sustainable, there is a tool. So their predictions was right. It's a next generation process simulator for chemical engineers. So that's a history of process system engineering, but where does it fit in the process development? So if you have an idea, so it shows a life cycle of a chemical industry. So as we said, like the chemists used to find things by accident or by intentions in the lab. Okay, they suddenly found, okay, I can produce certain product from the raw material. So that's a finding in the lab. Once you get that idea, what they do, they repeat the experiments to confirm it. Okay, it's not just by accident for one time, but it's a truth, or it's happening again and again. So that's a concept that you can carry forward. Then they started to make a lab scale setup a little bit bigger than a pilot scale setup. That's how they develop it to the industrial scale. So that portion is called research and development. And thereafter comes a concept called conceptual design. So what happens in the conceptual design, that's where the chemical engineer or an engineer steps in. So as I said, about the history of the chemical engineering, then you have to really think about how to produce this thing that they found in the lab in large scale. So that's a conceptual design. So then also we see the flow sheet. It's not only the reaction that happens in the beaker, but it's the auxiliary steps, pre-treatment and post-treatment steps. So what is the best combinations to put these steps together so that you can produce things in large scale to make profit, and also to run the operation safe, and other different criteria. We'll discuss about it in the next slides. So that's where we develop the concept. So not it's a concept. So that gives an input for the construction. So here the construction of the plant. So before the construction, there will be a detailed engineering design. So the input we get from the conceptual design, because conceptual design, we develop the flow sheet. Then we try to quantify the flow sheet. So with that values, you can design your equipments, you design the auxiliary equipments and everything. That's what something you will have in your final semester, the plant design or the process design. So with the detailed engineering design, you get the complete list of equipments that you need to purchase to start construction of the plant. Then you construct the plant. Once the plant is ready to run, there's a startup time, which means like you design your plant for a certain capacity, let's say 50 kilotons per year, but you cannot run it for 50 kilotons per year from day one. You have to really start the plant, see whether everything is working as they're supposed to be, and then you slowly increase the capacity to the design capacity or close to the design capacity. So that's the startup and commissioning step. So it takes some time to reach the design capacity. Then the plant runs for its lifetime. When it's done, it's a final phase, the decommissioning of the plant. So where the process system engineering comes, it's mainly in the conceptual design phase. So as we just mentioned in the last slide or the slide before that, that's to predict. You have an idea in the lab and you're predicting how this process would be in large scale. And also other advantage of the conceptual design, it's giving input on either sides. First of all, it gives input to the detailed design. Also, it gives input to the research and development. For example, when you get this idea in the lab, then you do further experiment to see what are the favorable conditions and what are the other possible protections. For example, you found a product, well, could there be other byproducts too? All these things are there. But the conceptual design can actually support enough information to speed up your research and development in order to scale up your process from the bench scale to pilot scale, and then finally to the industrial scale, because we have the limitations to do experiments for everything, because it's really expensive. You cannot just make an experiment without the proof. So in the conceptual design, as I said, how would the process behave if it was constructed? You don't have, you didn't build the system yet, but still you can predict the system. But how? We'll discuss about it. But just to get an idea about what's the significance of conceptual design in overall development process of an industrial production system. This is a cutting from Shell's website about their biggest engineering project in Qatar. That's called PIL. Yeah, it's a gas to liquid plant. So what they say, if you read over here, if you can read, otherwise I'll read it for you. It took 1 million hours, the equivalent of 500 years of full-time work of one person. So that's the time they took for the conceptual design. But it took 500 million years. So it's 500 times more is the total production time. So for the entire plant, we spend most of our money and time over this period of time to construct the plant, to operate it, and also to do the engineering design. But the conceptual design, you spend way less money because you don't purchase a lot of stuff. So it's a study that you do mostly virtually without building a system. And also you do it for a short period of time compared to the other development phase, but still it's quite long. The 1 million hours or 500 years of full-time work of one person. But it has a huge impact because any head start you make in the conceptual design or anything you find in the conceptual design, that saves millions or billions of euros for what's happening for the rest of the case, because you spend a lot here, but your decision-making step is over here. But any error that you make or anything that you didn't find that would affect your process in a bad way, like that causes a loss of not only the money or maybe other losses too. So this conceptual design is very significant, and we have to make right decisions or correct decisions in order to drive the rest of the process development faster and also most efficiently. So if someone asks me or anyone how to define this process system engineering, it's like you're asking someone on the beach to define how you define sea. So they define it in a different way. That's a pool of blue water. That's where the sun sets. So because it's huge. So it's the same thing. So process system engineering is a subdiscipline of chemical engineering. So this is the definition of Professor Sargent, who is a father of process system engineering. So he says it's all about development of systematic techniques for process modeling, design, and control. So why these three things, will come to that. Then there are two parts he further explains. One, some formulated tools. I'm not going through all the terms. Some formulated tools to predict the system. And the others, actually, they use these tools to get a deeper understanding of the fundamental concepts of the system. So these are the two main outcomes from the process system engineering. One, there are tools to predict. Second, we get more fundamental understanding how process works, because we have a huge limitations to do everything in real life or to do all the experiments to learn more and more about the fundamental concepts. So while only modeling, simulation, optimization, and control. So as I said, this term was proposed in 1982, but these practices were already there: process modeling, simulation, optimization, and control back then. So they just put them together under the umbrella of process system engineering. Uh, so maybe you know about the subjects. I see in your syllabus you have process modeling and simulations, you have process optimization, and also instrumentation and process control. So to get an idea, for the sake of discussion, I had a simple example. So there are two equations. You see it's a performance equation for a continuous tube-tank reactor. There's an Arrhenius equation that shows a relation of a rate constant with temperature. We talked about activation energy at the beginning, right? So that comes here. So this equation, so the first part of the process modeling, it's a process of representing your physical system in terms of equations. So actually, this equation that represents the continuous tube-tank reactor, so that really connects the volume to the conversion. So and here it actually, the rate constant is over here, so you can say the volume is connected to the temperature, the operating conditions. So it's sort of representing your actual system. So that's a process modeling. You write things in terms of mathematical terms that represent the physical system. And the second part is a process simulation. It's nothing but you have the equations right now. So you try to solve these equations for different inputs. For example, here for the sake of the discussion, I say you give different values for the temperature, calculate rate constant, and if you know what's the feed going in, what the conversion that you expect, you can calculate the volume of the reactor. So you can give different inputs for the temperature and see what is a required volume. So maybe technically what I'm saying is not going to be correct, but for the sake of discussion, now you have different values for temperature and the volume, but you cannot run your plant at multiple operating points. So there comes a third step, process optimization. You need to select the best among the alternatives. So you have these alternatives. For example, if I say one of them has a minimum volume. So this is a minimum volume. So we have an objective to minimize the reactor volumes, then we choose the corresponding temperature. So that's your optimum temperature. And there comes a final step, process control. That's while running the plant. When you run the plant, you need to keep this variable at that optimum. So when there is a deviation, you have a control that really sets this variable back to its optimum using a manipulated variable. So that's what you learn in the process control. So these practices were already there from the beginning of chemical engineering or production process. So they just group them under the umbrella of process system engineering. So this is a history of the process system engineering. So first we talked about chemical engineering. So there was a goal after industrial revolutions to meet the quality and quantity of the product. Then chemical engineers evolved to produce things in larger quantities to create profit and also meet the needs of material and energy. And then they became aware of the resources or to the need for making the process more efficient. That's where the process system engineering comes. So they also they are actually thinking about making it more efficient. So there was a challenge in both times. First, it was the need arose after the industrial revolutions, and the second one was a need to make things more efficient. But we are going to talk about. I'm currently talking about the engineers of tomorrow. So let's see what are the current challenges. What are the challenges we face right now? So challenges are not really different, but they're really significant right now. The first one, our population is really going up, especially you see it keeps on increasing and it expect to go on that same trend and the population will increase further. But you can see some couple effect that also we are experiencing on our daily life. So one is a fossil fuel consumption. With the same rates as the population goes up, the needs for material and energy will go up too. And also with this, all these technological innovations. For example, like maybe 10 years back when we were doing bachelor's, or before that, we had hardly one phone with us, or we didn't have a phone, mobile phone. But now maybe we have at least one phone, so our material consumptions are increasing with the technological innovations, and we use it more, and we purchase it. Like back then people were using that small Nokia phone for 10 years. Now like in 2 years people are changing their phone. So it's like with the technological innovations and with the population increase, our demand for material and energy keeps on increasing, and we still depend primarily on the fossil fuels. And one of the main consequences of that is a global greenhouse gas emissions, or the CO2 emissions. So as we have an increased consumption of fossil fuel, it also, you can see here, there's an increased consumption of CO2 capture. So this actually kind of coupled effect. I don't have to see you the pictures of global warming effects, because all of us, it's like coronavirus right now. Everyone is experiencing it by floods, or by high temperatures, by heavy rains, or whatever it is. Everyone is experiencing right now the effect of the global warming and the climate change. So what's our role? Why it's a challenge for us? Because the production process has a huge role in that. Why it's happening? Because we were actually following from the beginning a kind of a linear approach. We take things from wherever we get from, and we make things or produce things, and we take our environment for granted to dispose the remainings. It could be the unused product. It could be your waste that emit from your process, the emissions from the gaseous emissions, or the pollutions in water or soil, so other ways. So it's a linear process. So we actually need to change this approach. That's a current challenge, because how we are going to cope with, or how we are going to provide a solutions for what we face on our daily life with the global warming effect. So there are two approaches. I'll go a bit fast now because we're running out of time. So this is the industry of tomorrow. While I'm saying it, there are two concepts. So if you look back to the history, first there was a need to make things in a profitable way, but at the same time, at larger quantity with strict quality. People were not worrying about anything else back then. Then there was a need to make things efficient, so that economy would be further improved, and you can do a better management of the resources. And now for the grand challenges that we face now, there are two terms that we should keep in mind. One is a circular economy. Of course, we need to make profit, but in a circular way. I'll come to that. The second one, sustainable development. Of course, we need to develop further, but in a sustainable way. Economy is a part. So economy is an integral part of an engineer, so there's no dispute on that. So if you go to the first concept, you can see three terms: reduce, reuse, and recycle. So reduce means to reduce the consumptions of the resources. It could be the energy or material. So that's already sort of people are aware of it from the 1970s. So they were trying to make things more efficient, so that they improve the yield. So they use less raw materials, less energy resources, and so on. And reuse is also, to some extent, that's a part of our process to make it more efficient. For example, in a solvent-based separation process, you try to recover your solvent and recycle it, so that you don't need to use a fresh stream of solvent all the time. So that's kind of reuse within the process. And recycle is a part, like it's still a missing link, because you don't know what's happening with this product that you use. For example, the plastic is produced from the chemical reactions that ends up in different end products, and finally it's down to the earth. So there's a huge problem with this plastic waste. So how to recycle this? So that's a part that we really need to focus. We really need to widen our scope to see what's the impact of our process. And same over here, economy. So I just talked about the environmental issue with the plastic problems. We should really take care of the impact on the environment when you think about making your process better, and also the social community. How does it affect the public? And maybe an interesting cut again. It's related to Shell. There was a controversy. They found a new oil and gas reserve in sea, somewhere in the coastal area of South Africa, and they were doing some seismic testing, and they're starting to exploring the possibilities over there. But actually, there was a huge protest against them from the people in that area, because they kind of a sea dependent people. They do fishing, and it's much related to their livelihood. But with the activities of Shell, they were claiming like it really affected their daily life. So it affected the public around the area. So now you have to consider, when you really think on the conceptual level, you need to consider not only the profit, not only to make it efficient, but also where everything that you use will end up, and what should be the location of the plant, whether it's going to make the livelihood of the people around that area better, or it's going to make it worse. Because that's a true thing. Because even here in the Netherlands, Netherlands is famous for using natural gas, because they have the largest natural gas reserve in Europe. So they explore natural gas from there. They also export it. That's a part of the economy too, to other European countries and beyond Europe too. So what happened in recent years, the area that they explore have been experiencing frequent earthquakes in the last 3-4 years. So there's a huge protest by the people to shut down this plant. I can imagine that the whole energy requirement of the country is still hugely dependent on this natural gas. If they stop it, they have to export it from other countries. So this is an issue that we should consider at the very beginning. That's the point. At the conceptual design, not after, like, you build up the plan, you do all the damage. Then if there is a tension between the public, or if it affects the public life, that's not a nice thing you should do as a socially responsible engineer. So thing is, the grand challenges of today, it's much more than before. So there are multiple criteria. We have not much time left, because we are already experiencing the after effects or the consequences of this global warming on our day-to-day life across the world. And also, the good thing on the other side, if you see the research and development everywhere, like, there are multiple solutions proposed at various levels of development right now. So there are multiple solutions or multiple options. There are multiple criteria you need to make your process designed to, and we don't have much time left. So the prediction has become so significant than ever before right now for the current or the future engineers. But how we do it? Don't worry about the diagram. There are a lot of things, so I'll help you to go through it. So this is actually the reason proposed multi-layer framework by leading process engineers to take into account this multi-criteria, to take into account multiple technology options, and also take into account environment and society together with economics for a sustainable development. So it's a three-layer approach. So first thing, if you see the inner layer, it's like 1908, like you produce things from the resources. You have a process where the reactions and the auxiliary steps, where you make use of the resources to produce things in large quantity and maintaining the quality of the product. That's 1908 thing. So in this diagram, on the left side, you see the resources or the raw materials. On the right side is the product. So from the resources, the process makes the products. And on the bottom side, you see the skills required for that, to do this activity, to do this design, let's say. And on the top, you can see the impact, where it's going to have an impact. So the first layer, we convert the resources to the products. Of course, here you propose with your basic engineering knowledge of basic core topics of process system engineering, or this is how I design the process to produce this product from the raw material. So that gives out a process, a model design, or some inputs to operate the plant and further analyze it. But if you go further up in a layer, there you see the 1980s thing. So there is a concern about the availability of the resources. So there's a concern about the demand of the resources. So you need to make the process more efficient. So what happens when you make it more efficient, you get improved products and also less waste. So here you're not worrying about the waste, but now you make things more efficient and you produce less waste. So for that, what tools you need, not only your basic core knowledge, but you need to integrate the advancements in the technology. So I forgot to put the expansion of this. So it's like artificial intelligence, machine learning, process intensification, and so on. It's like you need to make use of, let's say, the artificial intelligence that would help you to predict like what could be the possible byproducts, let's say. So if you make use of this technology to limit those byproducts that will end up in giving out less waste to the environment. So the impact is it makes things efficient and also more sustainable. You take into account the environment around you. That's so more reliable. And the final layer, that's where it consider all the things. So you can see the impact that's for the towards the circular economy, or you take into consideration the society. But what you have to do then the skills you need, the main skill you need is to collaborate or to get more stakeholders. In that case, it's not only the engineers, it's not only the people of technology. Maybe you should talk to the local people in that area where you intend to put your plant, or you should talk to the policymakers, to the government, or to the government bodies to really modify their policies for the better things, or to involve them in the decision makings. So that's the overall inclusive approach. Like you consider everyone, not only the technical people, like, but everybody. What happens then? Then if you see the resources, you have to consider a lot of things. So where should be the location, what type of the resource? For example, now there's a trend to go for biomass, but biomass could be first generation, second generation, third generations. Like if you consider the first and second generation, the first generation biomass are the edible stuff. So like you can also use it for food. But so there is a controversy, like would it lead to food shortage if you use it for a large scale production process? Then you think about the second generation biomass, that's a non-edible stuff from the biomass, so it doesn't affect the food crisis. So this kind of thing. So you need to consider each and everything, and your problems become very big. Like you need to consider the whole supply chain, where your raw material comes from, how does it transport to your factory, then the process, and what happens on this side when you have a product, how it's going to affect the environment, what is the end product that people make from your primary product, and where does it end up, what's the entire life cycle of that product. So what happens with that, if you consider that, first of all, you can see who are the people involved in these processes who are benefiting from this. And also you can see the environmental impact of everything that you use in your plant. So it leads to an optimal product, the lowest possible waste, and controlled environmental impact. Because environmental impact is not just from the process of CO2 emissions, that from the process, but it could be there with the logistics to get your raw materials to the plant, and also the product life, where your product will end up. Will it end up in a sea, soil, or can you put it back in your process somehow? Like you recycle the plastic, for example. So if you can recycle the plastic, let's say if you gasify it, if you further use it for the same production process, it's called circular economy, because you're putting it back to the loop. And sustainable development of society, you consider the economics, environment, and also the society or the public. There's a lot of things, but the basic idea is this: at the moment, for today, for the engineers of today, there's a lot to consider, but we can actually consider that in a systematic way. We can find solutions for that. That's why the first definition of the father of process system engineering, he was emphasizing that it's a systematic technique. You have to do it in a systemized way by considering everything. So everything you do consider more things, problem become more complex. There will be a lot of elements, but things becomes more clear. But then we need talents. We need talents like to develop advanced tools, develop tools that simplifies this process and so on. So that's a current challenges that we all have in the process system engineering community. So let's come to you students right now. So now you're wondering, oh, why these graphs and all, like I'm just a BTech. Why should I worry about this? Because before or maybe 5 years back, this plain process system engineering was familiar to people when they joined their master's or PhD, when they go for their higher education. But now you see it should be a core part, as you already know the significance or the effect the conceptual design has on overall the production process and its impact on the environment and the society. So something you're already doing for the process system engineering, so you can do, I want to give you two tips. The first one, gear up with your concepts. So it's again, there's a three-layer approach to study. When you learn an equations, you can just do blah, 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 like that equal to that. And if you say it 10 times, you get it in your heart. You can really show it in your exam, but after the exam, it's gone. And the other way is to make it more efficient. So you use the tools like you can use equations in an application, for example, solve the equations, then you know, oh, these are the terms that in the equation, so this is how it's worth dealing with. So that's more efficient way to learn, and the most efficient way is the final layer. Like you have to team up with the people, you get your friends and teachers, then you're trying to make use of those equations for the betterment of society, for your projects that you have in the, I don't know what kind of projects you have, but the interesting thing I see in your syllabus, you have 4 sections of chemical engineering and society. I don't know what are the activities. I would like to know what you do, but maybe you can use these equations over there to see what kind of betterment it makes to the society. So that's a third layer. So you can already see that 3-layer approach is applicable to your studies too. But by focusing on this tip, so gear up your concepts, why it's important. So concepts, when I say about the concept, focus on this subject. So gear up the concepts of these subjects. Thermodynamics, so that's known as a predicting subject. So you can predict whether something happens or not. The reaction engineering, that's a core of the chemical engineer, where A is converted to B. So that's a core. Then transfer operations, mainly the mass transfer, that's a post-treatment part, where that defines the chemical engineers, or that distinguishes the chemical engineers from other engineers, because that's how chemical engineers maintaining the purity of the product. That's from the transfer operations. Then gear up your mathematics, both analytical and numerical techniques, because we need to solve these equations. So we are not just problem makers, we are also the problem solution providers too. So we need to solve the equations too. So just to tell you the importance of gearing up your concepts. So for example, this is a concept, mass transfer operations. So what happens in the mass transfer operation, you have a mixture of A and B, 2 components. Your objective is to separate it into 2 different streams of A and B, or A rich stream or B rich stream. So what happens in a mass transfer operations, I'm going too fast because of the time. We add a separating agent. It could be energy or material. For example, your distillation process. If you have 2 components, you heat them up. So due to their difference in boiling point, that's a physical property. When you introduce this separating agent, this component have a difference in their physical properties that lead them to kind of an intermediate phase, which gives you an A-rich phase and B-rich phase. In distillation, you get a stream in the bottom and top. More volatile would go up, and less volatile remains in the bottom. And you have physical means to separate them to A and B. So this is actually the concept. So if you gear up the concept, if you really go in a conceptual way, it actually make a good it makes your predictions more accurate. It helps you to save your storage space in order to deal with problems in a wider scope. For example, with this concept, you have the concept of the whole mass transfer, because when you think about distillation, you know what separating agent you add, what physical properties sort of responsible for the driving force. And when you think about the absorption, you just change the separating agent with the solvent, and solubility as a physical property. So that actually make you a good um, help you to predict well. For example, let's go to the conceptual phase again. So if you have two random components given, then someone asks you to predict what would be the best separation techniques to go for. You just look at their properties, then you see where you see the maximum driving force, where you see the maximum difference between these components, whether it's in melting point or boiling point or solubility. Then you can do the first prediction already. Oh, this is going to be absorption, it's going to be adsorption, so whatever process. So that's how the concepts will help you. So gear up your concepts. That's the first thing. Then I'm going very fast. And second, optimize your life. That's very important, to be optimistic, but more importantly, give more. How do you say, like, try to equip yourself better with the process optimization subject. I think you have that subject in the 8th semester, in the final semester. So what we do in the process optimization, very quick, we try to optimize a certain objective function. For example, in 1908, that was to optimize profit, and in 1980s, that's both profit and efficiency there, even though they're related. And now the current challenges, we have multiple objectives: the profit, minimum environmental impact, and the betterment of the society. So that's an objective. So we need to either minimize or maximize it, depends on what it is. Then it is always subjected to various constraints. Let's say you have constraints with your capacities, you have constraints with the emissions. That's why we have environment regulations when you design the plans. So a lot of things. So this is what you do in your whole process of process system engineering. So whatever it is, it's a process synthesis, design, analysis. There's a lot more to discuss in this field, but we keep it to this simple thing. So you can actually convert that into an objective, an optimization problem, where you define an objective, then you know what are the constraints, then you try to find the best variables, the axis, the operating variables, or the best process route to maximize or minimize that objective. So when you deal with this subject of process optimization, it's in 8th semester. I would like to see it a bit earlier, maybe in the 7th semester, 6th semester, so that you can also apply that to your problems that you learn in other subjects. But at that time, not only with the pen and paper, also try to get some hands-on with the softwares. So some of the softwares I would recommend to have some basic knowledge. I'm not saying you have to be an expert with that, but try to get some programming skills with Python or MATLAB even easier. Then Aspen is a flow sheeting software. Any sort of flow sheeting software like Unisim, what is available to you, and also the computational fluid dynamics software like COMSOL, ANSYS, and so on. So I'm not saying to be an expert by the end of your undergraduation, but try to get it some hands-on, some idea how does it work and what are its uses, and you will learn more when you go to your first job or for your higher education about it. So that was the last part. So I'm winding up here with some takeaway points. So when you study in your undergraduate, give more attention to the equations, because this is a part of your education. Whatever subjects you learn, you just deal with the equations, something equal to something. But try to appreciate more what are the variables and constants in the equations. Then you get an idea, okay, I have a hand, like I have some freedom to play with some of the variables, but not with others. Then you can see when you vary the one, you have control over how does the other one, or what's the impact on the other one. That's the outcome. I always say apply plus or minus 30% principle. When you vary this, then you can already see how sensitive are they from one to other, because this is kind of a basic skill that we do it like without even knowing, like predict things. So this will actually, this kind of practice in your education will help you to predict the consequences, as your student outcomes say, in both qualitative and quantitative terms. That's very important to predict it in quantitative terms too. Then you become a good process system engineer. So the conceptual engineers, also for every chemical engineer, this is required. And final and the most important is team up. Don't try to do things by your own all the time. It gives a lot of burden, especially during this time of pandemic, because we all, most of the time, we confined to our own space right now, a lot of time and a lot of tasks. So try to team up all the time. It helps you to collaborate first of all, and also you can divide the task. Nobody's expected everyone to do all the tasks or to find solutions for all the problems. So see what you are good at, or you can learn from others, how you can team up together to solve the problem in a most efficient way. Because at the end, you're not going to work alone. You're going to work in an environment where people from different disciplines, people of different background or different cultures or nationality are around you. So that's most important in your studies. And final slide, it's a summary, just a simple summary. As we say, the process system engineering is becoming more and more significant to address the current challenges, because we need to predict things. There are multiple options to go for the real solutions. So I expect more job opportunities. It's already there. It will only grow, the job opportunities with the process system engineering, especially all across the world. You will get access to anywhere. But the skilled engineers are required. Now there's a shortage of the skilled engineers to predict things in the conceptual design level. Also, the program I did, professional doctorate in engineering, it started in 1991 also. The main idea was they were really short of the design talents in 1990s in the Netherlands. So it's a special program in the Netherlands. So you don't see that anywhere else. So they wanted to attract the design talents all across the world. So after your master's, you can apply for this program. Then they give you a training 1 year at the university, send you to the industry in your second year to do a real project. So that's the point. Like, there's a shortage of the skilled engineers even now. Even I found like around 5 to 10% of the people working in that R&D are doing this kind of steps. So still there is a shortage. And to the young engineers, the nice points, because the new generations, right, they're love letters using algorithm, because it's a completely new generation. So for you, maybe it's not a matter to learn these algorithms or to learn programming, because you're different than us, but we are still young. So what we expect from you, because as you see, there are many challenges, but we need advanced tools. We need people who can really think differently to make things simple, to do it in a given timeline. So that should be the future for the engineers right now. And finally, gear up for the accurate predictions, not only with the technical stuffs. If you do this approach, like you can see what you are capable of. You can also predict more about like what you are going to contribute from your level, from your individual level, and collectively for the betterment of the society. And with that, I think that was the presentation. So I would like to thank especially the students to give their time for this presentation. I know it's difficult, the back-to-back online lectures nowadays. I'm also sure like you kind of fed up with the virtual sections because at the time you have to be really lively there in the campus. Should have some good time with your teachers, students, friends. But of course, we're all hopeful like we will come to that state again soon. So with that, thank you so much once again.
Thank you very much, Shijaz. It was really nice presentation. And the way you have presented various things related to the process modeling, simulation, and optimization, and how it is contributing to with the help of core subjects, that is very important. So rather, I would say the way you presented like degrees of freedom, right? whatever you have mentioned there, it was in terms of degrees of freedom. So like all you need to take care of your variables, your constraints, and you need to find out where you can work upon. So yeah, so team building is very important, and in that aspect, let's say one should work upon. So how to come up with your strengths and weaknesses. So that is very important for the students, and basically those who are in their let's say second year or third year, anyhow final year students, they are aware about their uh, the positive points or how they can implement their knowledge. So I think that is a kind of the thing which they have come up through this talk. So thank you very much. So I would like to ask students if they have any doubts in their mind, or if they want to ask to Shijaz sir, you may write in the chat box, or you may raise your hand. So we may have for next 5 to 10 minutes, we may have a discussion. Anything from your side, students?
So you can ask any. No questions are bad, so you can ask any questions. Like if you ask me how to come to Netherlands, that's also a good question. So you can ask me any questions.
Anything from your side?
So meanwhile, maybe I can ask a questions. So what's happening with the chemical engineering and society module in your syllabus? Like, because I see there are 4 sections. In 4 semesters you do this. It's a kind of a project, or what exactly are the activities going on there?
Yeah, it is a kind of project we are allocating to the students based on their interest. They are coming up with the literature. Actually, they are not doing a kind of project, but they are coming with the ideas or the existing problems, and they are
Mhm.
searching on it. That's it.
Okay. Yeah. So it's really nice because we don't see that in the syllabus or the curriculum of uh, most of the academic curriculums, because we really need to take into account the society early in the process development, also in the development of engineers. So that you're doing it in an undergraduate program is really nice. So I get some questions here. So in future there will be demand in PSC, yes. So that's what I just summarized, because our challenges are more. We have a lot of solutions in place, so it's a perfect time to predict things accurately. So there will be a lot. Oh, not in the future. It's already there are a lot of job opportunities in PSC. Uh, so the next question is someone really seeking for the job. Do you have any job vacancies for BTech chemical engineers? If you have a company, I would definitely hire you, but I don't have a company, so I'm still doing my research. I'm doing my PhD. Actually, I'm working on a technology called syngas fermentation. So that's a technology where we make the microorganisms consume the syngas. That's one of the main feedstock that we have out there to produce chemicals and fuels, but in a microbial way. So I'm actually working in the same field to predict what is the best way to convert this, and what is the best product and the raw materials, how it's going to make benefit to the environment, society. So I'm still doing my research in Delft University of Technology. But keep that spirit. Soon you'll find yourself in an environment that you can really help and aim. Is there any other questions?
No.
Yeah.
I think if there are any questions, I would like to ask students. So you may, meanwhile, you can give these questions to me, or I may float email ID of Shijaz sir with you. You may directly contact to him. So
Yeah.
anything related to if you want to go to Netherlands, or you want to share some your views as well in future. Actually, he is a good teacher and good friend as well. So don't worry about that. At any point of time, he will be there with us. I know that, right, Shijaz?
Yeah, always. So you can also see in LinkedIn we are connected. Me and Odessa, so that's a good platform to stay connected with people in the technology sphere. You can also see job opportunities first of all there, and you can see what's going on in the field. So if you don't have a LinkedIn account, start one, especially those who are looking for jobs in abroad. Like it's like an online resume. So if you have any LinkedIn, you can apply for a position in abroad. They first look at it, your LinkedIn. So you can stay connected to in the LinkedIn, and we'll be in touch if you come across the same stuff in the future.
Yeah. So I think we should conclude this session because we have other assignments as well, and even students
Okay.
they are having six sessions in a day, and that is the
Come on.
reason why that may be the reason why the many students, due to the lack of data, they may be not able to join.
So did you record this? You recorded this presentation,
Yeah,
right?
I started
Okay.
recording, but initially it was not started. So
Okay.
I started it
Okay.
when you started your discussion. So don't worry
Okay.
about that. Recording will be shared with you.
Okay. It's not for me. Maybe for the students who didn't join. But the presentation was not covered, right?
Yeah, yeah. We are
Okay. It's
going to
okay.
share this on our YouTube site, so it will be available for everyone.
Okay. That's fine.
Okay.
Okay. Then it was my pleasure to join you. That was a nice, motivating session for me as well. Just to refresh things while I'm working, just sort of self-reflection, and again to reconnect to my dear friend Dr. Ritesh Palkar, and also to see other faculties in your department and the students. So
Yeah.
all the best for the rest of the day and for the assignments and for all of the stuffs.
On my personal behalf and Department of Chemical Engineering, Faculty of Technology, Marwadi University, I would like to thank you, Mr. Haneef Shijaz, for his precious time. So he joined us all across from the Netherlands by taking his time and keeping his all the assignments away. And we were in touch for this program from last 1.5 months, and we planned it today. So though I was not feeling well from last 2 3 days, I am suffering from the viral fever. But today I thought we must do this. So that was the reason actually why to conduct this. So thank you very much, Shizal, for your words. I know this is very important to learn about PSEs and how important it is. I hope student has got the information about this, and they will learn more about when they will come across all the courses in their upcoming semesters. So thank you very much everyone for joining this session. So with the due permission of our head of the department and our today's esteemed guest speaker, Haneef Shijaz, I would like to conclude this session. Thank you very much everyone. Take care and bye bye.